Everybody sitting? I'm very happy to announce the next lecture from László Lovász, from the Abel Laureates to the mind HTM, if I say it well. I could give a long list of very impressive results, and parallel to that, a very long list of very impressive and prestigious prizes. But let me just mention one prize, Abel. That must be sufficient tonight, and I don't want to steal more time from László's talk, so please, László, take the floor.
Thank you, Lex, and it's okay. So, thank you, Lex, and I am so pleased to be here and meet so many friends and people whom I have known for a long time and worked with. So I'm really pleased to be able to give this talk today. I talked yesterday about so a rough idea of what graph limits are and what are they good for. So today I will talk a little bit more specifically about graph limits. Let me just very briefly summarize some of the older results about graph limits. If you take a sequence of graphs, so the idea is you take a sequence of graphs which in some sense look more and more similar, and then you would like to assign a limit object to this sequence, which will also look similar in some sense. For dense graphs, you can define a notion of local convergence, which is that you pick a subset of some given number of points, and you see what graph there is. So this gives you a distribution on, say you pick 100 points, on graphs with 100 nodes. And if two graphs, if you go farther and farther in the sequence, these distributions are becoming more and more similar, then you say that this sequence is convergent. And that notion was defined with Christian Borg, Jennifer Chase, Vera Sors, and Kati Westergombi. And it was also a closely related notion was defined by Rasborov about the same time. There are limit objects here, and the limit objects are graphons. And the graphon is just a measurable symmetric mapping of the unit square into the 0-1 interval. And in some well-defined sense, which I will very briefly come to, these graphons are the limits of convergent graph sequences. So, so graphons are, in a sense, in this sense, they are generalized graphs. They are, in a sense, and in a well-defined sense, the completion of the space of graphs. Of course, for this you have to define a distance of graphs, which I will not do today because I want to talk about other things. But since you are considering them as generalized graphs, you want to extend graph theory, as much graph theory to graphons as possible. And in fact, a number of basic graph theoretic constructions and facts have been extended: connectivity, matchings, automorphisms. Extremal graph theory is works extremely well in this infinite setting. So in fact, it helps a lot in extremal graph theory. Now there is also the bounded degree case where we look at so those were dense graphs. That means that a positive fraction of all pairs were connected by edges. This is the opposite end, where each node is only connected to a bounded number, say most 10 other nodes. And we could, and here you can define local convergence again by sampling. It's a little bit differently, has to be done. I don't want to go into it. And you can assign limit objects to these graphs. This was first done by Benjamini and Schramm, and it's called involution invariant distributions on rooted graphs. That's the limit object. And contrary to the dense case where the theory is complete, so we know exactly that every graphon is the limit of a convergent sequence, and it's essentially uniquely determined up to some measure-preserving transformations. In this case, the big open question whether involution invariant distributions are all limits. That's whether everyone appears as a limit. That has a lot of exciting connections in group theory. It would imply that every finitely generated group is Sophic. Let me not. So it's an old, important, open problem in group theory. There's another notion of convergence, first introduced by Bolobás and Riordan, which is, we call it local global convergence. I will not define it. It is just I would like, because I am focusing today on these limit objects, not so much on the convergence to them. So the limit objects here are graphings. Now, what is a graphing? It's a bounded degree Borel measurable graph with a certain measure preserving property. What does it mean? It's probably easier to see in this picture here. This is a graph in the sense that if I take a point here, then I look at, it's like the adjacency matrix of a graph, but the underlying set of the graph is again the 0-1 interval. And so, for example, this element of the 0-1 interval is connected to altogether to five other points. So it's a bounded degree graph, and the measure preserving means, if one special case where you draw these lines, measure preserving means that they go 45 degrees. Let me again skip the exact definition. And that was these limit that established that these are all limit objects by Hamed Hatami and Balázs Szegedy. And again, here we know that not all of them are limit objects, and we don't know which ones are limit objects. And again, if you think of these kind of graphings, these kind of special graphs, infinite graphs as generalized graphs, then of course you want to extend graph theory to graphings, and you can define matchings again, flows, expansion, edge coloring. So this is a newer area, and there is a lot of work being done on that, and there are some very interesting algorithms, for example, to compute matchings in them and so on. But let me go on. So these are the two extreme cases. And the question is what happens in between. For example, what happens to hypercubes? Hypercubes are not bounded degree, but rather sparse. Or incidence graphs of finite projective planes. What happens to stars? Those have high degrees, not bounded degree, but they have a linear number of edges. One subdivisions of complete graphs. There are many other interesting examples. Now it turns out that there has been some work done on these limit theories. There are the notion of LP graphon. This is general. So if the graphs are a little sparser than dense, then the limit objects become more complicated. So an LP graphon is, graphon is a function which whose values are between 0 and 1, which is bounded. Now an LP graphon is not bounded, but the function is in LP, so the pth power of it is integrable. And there is well, there are other notions. Frenkl introduced some other notion of convergence, and there's a limit object that's called graphoning, and shape convergence we introduced with Szegedy and David Kunszenti-Kovács, and that we call the limit object S-graphons, and then Backhausz and Szegedy introduced another notion of convergence. And what's interesting in this is that these objects are essentially all the same. So the limit objects are essentially the same. Now, when I say essentially, I mean that in each case there is some basic structure, which I will come to in a minute, with some bells and whistles, with some bells and whistles. So what is common in all of these limit structures? Well, first of all, there is always an underlying Borel sigma algebra. Usually the zero, you can identify it with the 0-1 interval, but that will not be always convenient. And you have a way to pick a random node just from the 0-1 interval, uniform distribution. In my talk yesterday, I explained that this is why your limit objects are never countable graphs, because that doesn't work with a countable underlying set. And you have a way to pick a random edge. It's a notion of picking a random edge. In the case of a graphon, it's a function, so you view it as the density function of some distribution, and then you pick a point from that distribution. And in the case of a graphing, again, you can pick it. I don't want to go into the exact details of that. And another common feature is that you can do random walk. So there is some kind of Markov chain behind all of these things. If you are here, so you do a random walk on the vertices, which are now all points in the 0-1 interval. And if you are at this point, then there is, you can view this as some kind of, after scaling, a density function of one step. And similarly here, it's a bounded degree graph, so the random walk is trivially defined. Now, these are all hints to the following definition. I now have to go into some formal definitions. So we look at some standard Borel sigma algebra, say the Borel subsets of the 0-1 interval. I denote by J the underlying set. MA is the set of finite sign measures on this. And on this sigma algebra, they form a Banach space with the total variation distance. I don't. I mean, it's just so that it's a reasonably nice set. If you have a mu on the unit square, so A cross A is the Borel sets of the unit square, then I denote by mu star the interchanging the two coordinates. And measure is symmetric, means that mu is equal to mu star. And if for a mu, I will denote the marginals of mu. So these are the measures on the two sides of the unit square, and S mu of J cross A and A cross G. Okay, so this is just some notation. Now, how do Markov chains come in? So here are three definitions. We know that the Markov chain, as we learn in college, is a sequence of random variables, so that Wi, well, I mean, very informally stated, Wi plus 1 depends only on Wi. independent of the earlier ones. A Markov kernel is a more complicated object. It is a sigma algebra, and for each element of the underlying set, we have a probability distribution on the underlying set, or on the Borel sets of the underlying set, which tells you how to move from this point. And there is a technical condition which says that if you fix a set A and you look at the probability that you step into A, that this is a measurable function of U. And the Markov space is actually maybe a somewhat simpler object. It's a probability measure on the square. So imagine, this is the unit interval. So this is the square whose marginals are equal. That's a Markov space. And what's the connection between these? There are some trivial and some less trivial connections. If you have a Markov kernel, so that means you know how to move from a point, and you specify a starting distribution, then this gives you a Markov chain, because you can follow the rules of the specified by the Markov kernel, create an infinite sequence of variables. If you have a Markov kernel and add a stationary distribution, you get a Markov space. Now, what is a stationary distribution? It's a distribution that's such that if you pick a point from this distribution and do one step, you get a point from the same distribution. And if you define, it's a measure eta on, well, you define in A cross B as the integral of PUB. So it's the probability that if you are in A, you step into B. But if you are in A, it means that if you are in the stationary distribution restricted to A, then you get this probability. So it's really the probability that the very long stationary random walk steps from A to B, how often it steps to A to B. So this is the ergodic circulation, and the stationary distribution turns out to be very easily computable, that it's just the marginals of this. Now, these are the trivial steps. The less trivial step is, it's still, if you Markov state plus no distribution, these are these notions that I have as graphons and graphops that have been introduced by different people as limit objects. Here is an equivalence, and I only showed you the trivial direction, so that if you have Markov kernel plus stationary distribution of Markov space. The other one is not so trivial, that if you have a Markov space, that means a probability distribution on the unit square, then you can go back to get a Markov kernel, but that's known from probability theory. Now, some examples. Graphons and graphings, I have more or less shown you why they are special cases. Here is a very interesting special case, orthogonality spaces. So I would like to consider these Markov spaces as generalizations of graphs. And for that is the question, is it rich enough? I mean, it's such a simple notion. You have just the unit square and a measure on it. Well, the two marginals have to be equal. Is this a rich enough notion to allow any non-trivial generalization of graph theory? So I I'm going to show that it is. I will show you how to generalized sampling and the notion of subgraph density to these spaces. And maybe I will have a little time to speak about how to generalize flow theory to these spaces. And there are other things, random walks, expanders, spectra can be generalized to these spaces. And there are some dreams that cut distance and Semeridis regularity lemma should be generalizable, but we have not done that. So what about subgraph densities? Now, in a finite case, we have this set, the set of homomorphisms of F to G, which is a set of all adjacency-preserving maps from the vertex set of F to the vertex set of G. If everything is finite, it's a trivial definition. And then there is the homomorphism density, which only works in dense graphs. You count the number of such homomorphisms and divide by the total number of all maps. So this is the probability that if you randomly map the vertices of F into the vertices of G, then this random map will preserve edges. That is this density. But if the graph is not dense, then this can be typically essentially zero. So you want to normalize with something which is also small, and and the good thing to normalize with is the edge density raised to the number of edges. So in other words, So if the edge density is very low, then you normalizing by it, you get something which may be possibly better measure for the trying to count homomorphisms. And this is a good notation. At least it can express, there is a famous conjecture, which is a Sidorenko-Shimonovich conjecture in extremal graph theory, which in this language just says that if F is a bipartite graph, then this normalized density is always at least 1. Now we can normalize in the graphon case, it's actually quite natural to scale this. It is not 0, 1 valued anymore, so we can scale it. We can scale it so that the total integral of Wxy is 1. And in that case, this T star or T can be defined by this integral. And that's the density of F in W. The integral is, let me quickly explain what this integral should mean. Here you assign a variable to every vertex of F. And then for every edge of F, you evaluate the function W at the values assigned to the edge and take the product of that. So if W is 0, 1 valued, which would correspond to some kind of graph, in that case, this product is non-zero, equal to 1, if this mapping of VF into the 0, 1 interval preserves edges. So if each of these factors is 1, otherwise it's 0. So this is in some sense, in some analytic sense, counts the number of homomorphisms. And then there is also, we can take this internal product and we can say that this is the density function of a measure on homomorphisms, which is a good thing to have such a measure on homomorphisms. So in the finite case, we talked about random homomorphisms, but in the infinite case, this is not trivial to define. Now, let me come to this interesting example of orthogonality graph. So the orthogonality graph is a graph on the unit sphere. I think of this as the two-dimensional sphere, but HD would be the same construction in dimension D. So this is H3 here. And let eta be the uniform distribution on orthogonal pairs. So this is like being able to select a random point, of course, because it's a very symmetric object, a random point of the sphere. And it's also a random edge can be selected because all the edges look alike, so it's also a symmetry allows this. Now, a homomorphism of a graph G into this has occurred in a completely different setting already, and it was called an orthonormal representation of the complement of G in this space. What does it mean? We map the vertices of G onto vectors, orthonormals or unit vectors, and we require that if 2 points are adjacent in G, that means they are non-adjacent in the complement, then they should be mapped onto an orthogonal pairs. But now we are, suppose that we have a graph, so can we define the density of a graph? And can we define a random copy of a graph? And if you begin to think about it, it's not so trivial. So this is really the following. First of all, for C3, it's easy to define a random copy because triangles are still all alike. So it follows that there is a uniform distribution on them, just by some hard measure. But here is the interesting example, C4. So suppose you want to map C4 into this orthogonality graph. You can start with mapping a vertex, say map it on the North Pole, call it the North Pole. Then its two neighbors must be mapped on 2 points on the equator. But now the fourth point must be mapped either onto the North Pole or on the South Pole, so on a parallel vector. Which means that the homomorphisms fall into two sets. One where one pair of opposite points are degenerate, and the other pair is fine, it can be anywhere, or the other way around. And so there is no natural notion of a random copy here. You can flip a coin and say that I decide that these two should degenerate or those two should degenerate, but you sort of feel that this is cheating, and indeed it's cheating if you go to more complicated graphs. So there is trouble with C4, and in fact it cannot be defined. Now with C5, it can be defined, and it's non-trivial. Now this is just to show you that things get fairly interesting. You can actually compute the densities of these modified star densities in the 3-dimensional, 4-dimensional, and so on, orthogonality graph, and you get these kind of interesting quantities. So far, everything we computed looks like a rational number times power of pi. I don't know whether this is a general fact or it's just for the simple cases, but that's how it turns out. Now, at this point, I would like to quote an old result, which I have with Lex Scriver and Mike Sachs. It says that G has an orthonormal representation in D dimension, in general position, so that the representing vectors should be in general position. No d of them, no d plus one of them should be, no d of them should be linearly dependent. That happens if and only if G is n minus d connected, or equivalently if the complement of G contains no complete bipartite subgraph on d plus one nodes. And that seems to be, this theorem turned out to be the key for what we could do for these, to construct these limit objects. Okay, so that means any d vectors are linked. This is just a translation of this. So it has that G has a homomorphism into this orthogonality graph, so that the image is in general position if and only if G contains no complete bipartite subgraph on d plus one nodes. Okay, that's a nice characterization, simple characterization. Let me just recall the idea of the proof, because that will be important. So we want to map G into the D space on unit vectors in D space. Each node should be uniform on the sphere. And it should be orthogonal to all previous neighbors. So as you take, well, I should say uniform on the sphere, conditional on being orthogonal to the previously mapped nodes, because we have to maintain orthogonality to those neighbors which we have already mapped. And then we show that this distribution of this map, that's a random map, and in the paper we showed that it is independent of the order that we did. And then several years later, Odette Schramm and Van Wu noticed that this was wrong. So there was an error in this proof. But luckily we could fix it. And we could fix it by showing that it's, even though it's not independent, if you have these two orders of the points, this gives two different distributions on these finite strings of nodes, of vectors, then these two distributions are mutually absolutely continuous. So they are absolutely continuous with respect to each other. And once you have that, the theorem is fairly easy to prove. Because then if you want to, the issue is the general position. And we have seen in the case of the four cycle that this is a non-trivial issue, the general position. And then you can start with whatever subset D set you are interested in, and then you can put this at the beginning, and for the beginning it's trivially general position, and then you go on. And now to get actually the numerical values of densities and so on, we have to figure out Radon-Nikodym derivatives. And that's that you can do. It's some kind of complicated things, and that's where the pi's come in, and that's why this complicated formula. Now, again, now the surprising thing is that this looks like very, very geometric, but then it turns out that it generalizes to a very, very wide class of examples. Recall that a Markov chain is just a Borel sigma algebra with a measure which is, and now I will assume it's a symmetric measure, symmetric probability measure, so that generalizes undirected graphs. And let G be a simple graph. Now, you want to find all homomorphisms of G into this Markov space, but now there is no underlying graph anymore. You only have this measure. So the edge set is replaced by just a measure on all pairs. So the home set should be replaced by a measure on all maps of the vertex set into the underlying set of the Markov space. And so the question is how to define this measure. I will just state the result. We would like to get this measure, and the way to go eventually we found is to axiomatize. What do we want from this measure? So once again, given eta, this is this Markov space. It's just a symmetric measure on the unit square. And you would like to define eta to the g. So that means the measure of all maps from g to eta. And then there is a technical, there is some trivial starting for the 1-point graph, it should be pi. For the 2-point graph, it should be eta. And the margin, this is a technical condition that the marginal of graph should be absolutely continuous with respect to whatever measure you construct for the subgraph. And this is the interesting condition, the Markovian. It says, I explain it in this picture, that if you fix, so this is G and this is two subsets of G, such that there is no edge between the outside, between U minus W and W minus U. And now the condition says that if you fix, you want to map this into this whatever Markov space. If you fix any map here, or almost any map of the intersection, then the extension to U and to W should be independent. This is very similar to what probabilists call a Markov random field, but it's not exactly the same as a Markov random field. It's a little bit stronger condition, but and then it turns out that this is the right set of conditions, except I need to introduce one more condition. And this is actually a very simple condition, and I wonder if it must have come up in probability theory millions of times, but I haven't found a reference to it. So you pick a random, so this is basically about a Markov chain. You pick a random point from the stationary distribution. You make k independent Markov chain steps from this random point. And now you look at the joint distribution of these k images. So this one and the same point, and you take k steps. You look at the joint distribution of the results of these steps. And if this is absolutely continuous with respect to pi to the k, that's what you would get by choosing k independent stationary points, then we say that this Markov space is k-loose. Okay. Yeah. Graphons are k-loose for all k. Graphings are one loose but never two loose. And this orthogonality is Markov space on the two-dimensional sphere is two loose but not three loose. If you pick a point, make two random steps, and you forget then about this starting point, and these 2 points can be anywhere, any pair of points. So you have to check that densities are finite. But if you make 3 steps, then they will all be on the equator, so the resulting 3 points will always be linearly dependent, and so this is not, so they will degenerate. And so the theorem is that if you have a k-loose Markov space, then for every graph with girth at least 5, and degrees at most k. And there is a way to define, associate with it this measure on homomorphisms so that it is normalized, decreasing, and Markovian. So it satisfies the axioms that I posted. Okay, let me skip that. How much time do I have?
Around 7 minutes.
Okay, so just to add to the previous thing, it really is not easy to define what a random copy of, say, a pentagon in the orthogonality graph is, or these are somehow rather tricky things to do, and I think that it should have some interesting applications, because these the measures have very nice properties that we constructed. But now the main goal is to convince you that these Markov spaces are interesting. They are non-trivial and they are good generalizations of graphs. And there is a graph theory, there's reasonable extension of graph theory to them. So very briefly, I would like to talk about extending some flow theory to these. And let me start with circulations. So here is a finite graph case. If a circulation is defined as an assignment, well, this is a directed graph. Usually it's assumed that, yeah, so let's let it be a directed graph. And to every edge, we assign a real number. And the condition is that the sum of values entering a node is equal to the sum of values on the edges leaving the node. That's called the flow condition at that node. And if there is an assignment which satisfies this flow condition on every node, that's called a circulation. Now, how to generalize a circulation? Well, there are circulations that have been generalized to usually considering function on pairs of points, and but it's not. There's a more natural generalization where you want to consider this this assignment of values not as a function on edges, but as a measure on edges. Now, in the finite case, that's the same thing. A function is a measure, and vice versa, a sign measure, vice versa. But here it's better to try to generalize it as a measure. So circulation should be a measure on the pairs. So again, it's a measure on the unit square. And the flow condition simply translates that its two marginals are equal. The first marginal is the inflow, the other marginal is the outflow, so the two marginals should be equal. And similarly, you can generalize the notion of a flow from a point S to Ts, except that the difference of the two marginals is non-zero in those 2 points. So they are you get a Dirac measure in those 2 points. So a Markov space itself is just a circulation, non-negative circulation, which is normalized. So this is the definition of a circulation. And now let me just translate one fundamental theorem in flow theory. It's the Hoffman circulation theorem. So in finite graphs, the Hoffman circulation theorem is about a circulation where for each edge, the flow value on that edge has a lower bound and an upper bound. Now that generalizes very nicely to this setting. You take two measures on on the square, then there exists a circulation. You want to find a circulation alpha between these two measures. So one is a lower bound, the other one is upper bound. The theorem says that such a circulation exists if and only if there's a trivial condition that the lower bound should be less than or equal to the upper bound. And there is a less trivial condition which says that the lower bound on the set of all pairs going from X to the complement of X should be less than or equal to the upper bound on the set of edges going back. It's very easy to see that this is a necessary condition, but it turns out also be a sufficient condition even in this general setting. In the finite case, that's exactly the Hoffman circulation theorem. The proof of this is not terribly hard. You have to use the Banach theorem. Now, flow theory actually turns out that it has natural generalizations of many things in flow theory. Max Flow-Min-Cut, very similar. Flows can be decomposed into paths. That's the important tool in finite case. It remains valid. You have min-max formulas for minimum cost flows and minimum closed circulations, generalizing the finite case. There are integrality theorems, which I don't have time in the finite case, which remain valid. Actually, that's something which is a bit tricky, because in the finite case, these integrality theorems are usually argued about the total unimodularity of the incidence matrix between directed edges and nodes. And doesn't work in the infinite case. You have to find another proof. And there are some even multi-commutative flows theorems have generalizations to this setting. So I will stop here. I wanted to, really my main goal was to call your attention to this interesting object, which is simply a measure on a square. that this object has a lot of, is a generalization of a, well, if the measure is symmetric, then of an undirected graph. And these undirected graphs are, and these suggest a lot of questions about these measures. And if you do it carefully, then you get very non-trivial generalizations of subgraph counts and other similar issues. Thank you very much.
Thank you very much, Lottie, for your very nice lecture. And it seems all symbols did their work.
Yes, yes.
So,
yeah.
that was very nice. Questions? Sorry, I don't use the microphone. Are there any questions?
So, at the very end, you said, just summing up, you said, okay, so these symmetric measures are good models for graphs. So I was wondering, does this also work if we don't assume it's symmetric as a model for directed graphs, or does that fail dramatically?
Yeah, I think it works. It works. There is, sometimes it's better to consider it as a generalization of bipartite graphs, but of course, even in finite case, you often go between directed graphs and bipartite graphs with an identification of the two color classes. Yeah, so for example, this Hoffman theorem is really about directed graphs, because flows are defined in terms of directed graphs.
Any other question? There. Yeah.
So yeah, if you could choose something that you would see the proof of in the next 5 years or something, what would it be?
Oh, well, I formulated the Sidorenko conjecture here, which says that, I mean, it's actually about finite graphs, can be formulated with finite graphs, so that it says that if you count homomorphisms of f into G, then where f is bipartite, then this is always at least the number of homomorphisms, and you can say that it's like you replace f by the same number of disjoint edges, so by a matching. And that has a certain number of homomorphisms. And the conjecture says that this is always a lower bound. And I formulated it differently, but I didn't have the time to come to this, but this seems to be a very crucial element of many possible extensions and generalizations and so on. So I think this is a deep conjecture. People have worked on it for several decades.
But elementary to understand.
It's an elementary conjecture, very easy to understand.
Yeah. What is the problem?
But there are highly non-trivial results about this. So people have proved it for many classes of bipartite graphs. So, but the general is a little bit elusive.
There was,
Yes, you mentioned about the Meredith regularity lemma and the Kautsky lemma, and then it needs a notion of pseudo-randomness. And how would you define this notion for this Markov measures? Do you know already?
Actually, that is rather natural. You want to partition it, the space, so that if you in each of these partition class average out the measure. So you take the measure of the partition class divided by well, let's assume that the marginals are the uniform distributions. So if you average out, so you replace it by a constant density on each of these squares, then you want to have as little change as possible. And at the moment, we haven't come up with the right notion of making as little change as possible. But the pseudo-randomness should mean that in some sense, the measure itself should be pseudo-random, should mean that in some sense, it's close to the product measure.
So it's close to the product measure on each one of those sets, but then the notion of closeness is not trivial.
That's not trivial, and we haven't been able to come up with something which is true and it's useful.
Okay, thank you.
There is another question.
Mine was related to the previous one. Basically, so you talked about a notion about generalizing graphs to this Markov chains. And so my question is, do you have a topology on this space of Markov chains on the squares that makes interesting objects continuous, like the graphon does? Or do you expect to?
That's a very excellent question, because it allows me to formulate one of the conjectures or open problems that we have tried hard to solve and we failed. And the question is, okay, you want to introduce a metric on J, so on the side of this. Now, if you take 2 points, they are at a certain distance. Now you take a step from each that gives you a probability distribution on the lines above them. And now you can define the Wasserstein distance, if you know what this means, of these two. It's really a minimum matching problem between those two. So these are two probability distributions, and there is a notion of distance between them. And so you want to find up the matching. And what would be nice, the conjecture is that you can define so this is a mapping of a metric space into another metric space. And if this is continuous, that would be the nice thing to do. And that can be done in the graphon case and in the graphing case, many other special cases, but we don't know it in general.
Just a few questions still.
Yeah, maybe this is again a continuation of it. Like in the graphon case, there is a nice self-adjoint operator related to the graphon, which gives the spectrum. Here, is there a nice operator which kind of gives information about the spectrum also?
Another very relevant question. Yes, there is an operator. You can always define an operator from, say, L squared of the stationary distribution to itself. This operator is what was called graphop there. And the idea is what is interesting in connection with this, that in all cases which we could handle, this is not always compact. On graphons, it's a compact operator. On graphings, it's not a compact operator. It seems to be very relevant whether this operator is compact, but we don't have any theorems around this. It just seems that those are the cases which can be handled. So for example, on the sphere, it is compact.
Maybe a last urgent question?
Thank you for your presentation. I was wondering, are you familiar with the applied fields of graph signal processing and graph-based tracking, and what would your theory mean for those applied fields?
I am not really familiar. I mean, I am familiar in a superficial way. It is one of the possible directions to take, is to use graph limit theory to. I think this question came up yesterday too, when there is some kind of dynamics on the graph, but there are only sporadic results in this respect.
Okay, let's stop here. Possibility in the reception for asking more questions. So thank you once again. Let's see.